The central limit theorem. The central limit theorem states that the sampling distribution of the mean approximates a normal distribution, with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of n, where n is the sample size. If the sample size n of the random samples is large, then we can use the central limit theorem, meaning the sampling distribution of the mean will always be normally distributed as long as the sample size is large enough. Thus, we have this comparison. Now, a random variable x is approximated by a normal distribution with a mean mu and a standard deviation sigma. And our standardized formula for this one to get the z-score is this one. Now, since we're talking about the sample means, so we can just substitute some values from here. No? So we're talking about x bar. This will be approximated, therefore, by the normal distribution with mean mu sub x bar and the standard deviation sigma x bar. So therefore, with this central limit theorem, mu sub x bar is equal to the population mean and sigma x bar is equal to the population standard deviation divided by the square root of the sample size n. Therefore, our formula now for our z will also change. Our x will become x bar, which is the sample mean, minus the population mean divided by our standard deviation divided by the square root of n. So this will be our formula for the central limit theorem. Now, how large should the sample size be? When n is greater than or equal to 30, the central limit theorem applies. The sampling distribution will approximately follow a normal distribution. When n is high, the standard deviation is low. There's not much spread in the sample's means because they are precise estimates of the population's mean. Generally, as sample size increases, the sample mean tends to be normally distributed around the population mean and its standard deviation also decreases. Now let's solve some problems. The average cost per household of owning a brand new car is 5,000. Suppose that we randomly selected 40 households. Determine the probability that the sample mean for these 40 households is more than 5,350. Assume the variable is normally distributed and the standard deviation is 1,230. Now take note, we have encountered already two formulas. Now take note, if we're talking about the sample means or samples, we will use this formula. If it's not about the samples or the sample mean, then we will use this formula. Now going back to the first example, the question here is we need to determine the probability that the sample mean. So it talks about mean, so the sample mean x bar. So meaning we can use now the central limit theorem, especially also that our n also is 40, which is greater than or equal to 30. Now let's write first the given. The population mean is given on the first paragraph, first sentence, I mean. So we have 5,000. Then we have n equal to 40. And then the standard deviation is 1,230. Now we are asked to find the probability that the sample mean for this 40 household is more than 5,350. Okay, so let's solve. So we will transform that one to z, but we will use the central limit theorem formula. So this is equal to 5,350 minus 5,000 divided by 1,230 divided by square root of 40. So let's compute 5350 divided by 5000. I mean minus 5000 divided by the fraction 1 to 30 divided by square root of 40. And the answer is 1.799 or 1.80. So meaning it's greater than 1.80. Now, so let's draw the normal curve. Okay, say for example, we have this normal curve. We have 0. 1.80 is positive, so here on the right side. It's greater than, so the area is here, so the probability is this shaded part. So meaning our formula here with our table is 0.5 minus what is 1.8 is 1. 0.4641 So 0.5 minus 0.4641 is equal to 0.0359. So therefore, the probability that the sample mean for these 40 households that is greater than 5,350 is 0.0359. So it's very small. Number 2. The average age of a car registered in the LTO is 10 years, or converted to 120 months, assuming the standard deviation is 20 months. If a random sample of 35 cars is selected, find the probability that the mean of their ages is between 115 and 129 months. So this time again, we're talking about the probability of the mean. So again, we'll use the central limit theorem with n equal to 35. And our mu is 120. And our standard deviation is 20. So we are asked to find the probability that the mean of their ages is between 115 and 129 months. So we will convert this one using the central limit theorem formula. 115 minus 120 all over 20 over square root of 35. So this is now z. So we have 129 minus 120 over 20 over square root of 35. So let's compute. So this one is equal to 1.48. So negative 1.48. And on the right side, we have 2.66. Okay, so one of the z-scores here is negative, the other is positive. So we'll just add their respective areas from the table. So negative 1.48, so 148 is this 4306, this one. So 0.4306 plus 2.66. Okay, 4961. Okay, so if we add this, we have 0.9267. 0.9267. Now, look at this. We add these two areas because the first number is negative 1.48, which is on the left side, and the other one is 2.66. So this are the, or this is the area. So that's why we add these two values. So therefore, the probability that the mean of their ages is between 115 and 129 is 0.9267. Next, the average number of liters of fresh milk that a person consumes more than 16 liters per month is 18 liters. Assuming that the standard deviation is 4.5 and the distribution is approximately normal, find the probability that a person selected at random consumes more than 16 liters per month. Now, take note, in this problem, it does not talk about the mean or the sample mean. Okay, so we'll just use the ordinary or the first part of our z-score, normal distribution. Okay, so our mean, population mean is 18 liters. Our population standard deviation is 4.5 liters. And we are asked to find that a person selected at random consumes more than 16 liters per month. Okay, so I mean, since this is not sample, about sample, so X. So we have this. So using our previous formula, so we have 16 minus our population mean is 18 divided by 4.5. So this is therefore equal to negative 0.44. So negative 0.44 is here on the left side of 0. So if we shade this one to the right because it's greater than, so this is 0.5 plus the area of 0.44. This is the area of 0.5. Okay, 0.5 plus this area. So 0.5 plus 0.44 area of 0.44 for 17. So 0.17. So therefore, our answer for this one is 0.67. So the probability that a person selected at random consumes more than 16 liters is 0.67. Next, letter B. If a sample of 32 individuals is selected, find the probability that the mean of the sample will be more than 16 liters. So this time mean. And also we have our n to be 32. So therefore, since it talks about mean, so we will use our central limit theorem formula. So more than 16. So this will become z greater than 16 minus 18. 18. So the denominator is, the standard deviation is 4.5 divided by square root of 32. So what is this equal to? .51. So this is equal to negative 2.51. So let's draw the normal curve. 0, negative 2.51 is here, and then greater than, so this one. So therefore we have 0.5 plus negative 2.51 is equal to 0.4940. 0.4940. This one. Okay, so therefore the probability is equal to 0.994. Okay, the probability that the mean of the sample will be more than 16 liters is 0.9940. Next example, a population has a mean of 75 and a standard deviation of 17.4. A sample of 35 items is randomly selected from this population. What is the probability that the mean of the sample lies between 72 and 79? So again, the probability that the mean, so it talks about the mean. So we'll have the central limit theorem with n equal to 35, population mean equal to 75, and the standard deviation is equal to 17.4. And we're asked to find this one, the probability of the sample that lies between 72 and 79. So we'll use the central limit theorem formula. So 72 minus 75 divided by 17.4 over square root of 35. So z, so we have 79 minus 75 over 17.4 over square root of 35. So let's compute this one. And 4 divided by square root of 35. So negative 1.02 for this one. Then on the other side, 1.36, positive 1.36. So the other one is on the left side. The other one is on the right side. So therefore, we will add the areas. So 1.02 is this 3461 plus 1.36, this one 4131. So add 0.3461 plus 0.4131. We have 0.7592. So the probability that the mean of the sample lies between 72 and 79 is 0.7592. Next, number 5. An electronic company in Laguna manufactures resistors that have a mean resistance of 120 ohms and a standard deviation of 13 ohms. So this is our population mean and this is our population standard deviation. Find the probability that the random sample of 40 resistors will have an average resistance greater than 114 ohms. So it talks about the mean, and n is greater than 30, which is 40. So we'll have the central limit theorem. So x bar is greater than 114. So this is equal to 114 minus our population mean, 120, all over 13 divided by square root of 40. This is equal to 13 divided by square root of 40. negative 2.92. So this is P, probability of Z greater than negative 2.92. Okay, so if we draw the normal curve, negative 2.92 is here. So greater than, so all of these. So again, this is 0.5 plus the area of 2.92, which is equal to 0.4982. So therefore, the probability is 0.9982. So the probability that a random sample of 40 resistors will have an average resistance greater than 114 ohms is 0.9982. Next, the mean serum cholesterol of a large population of overweight adults is 220 and a standard deviation of 16.3. So this is our population mean or our mu, and this is our standard deviation. If a sample of 30 adults is selected, then find the probability that the mean will be between 220 and 222. So meaning again, this is still about the central limit theorem because it talks about the mean. So let's convert. So we have 220 minus 220 over 16.3 divided by square root of 30. And we have z. So 222 minus 220 over 16.3 divided by square root of 30. Okay, so obviously the first one is 0 since 220 minus 220 is 0. So automatically that's 0. Then the other one is equal to 0.67. So if we draw this one, so this is just from 0 from our mean to 0.67. So meaning we can just go directly to our table. So 0.67 because this 0 is just 0. So 0.67 2486. So this is 0.2486. So the probability that the mean will be between 220 and 222 is 0.2486. 7. The average age of accountants is 43 years with standard deviation of 5 years. So this is our population mean and this is our population standard deviation. If an accountant firm employs 30 accountants, find the probability that the average age group is greater than 44.2 years old. So again, average, so it talks about the mean. So greater than 44.2. So this is equal to z, probability of z greater than 44.2 minus 43 divided by 5 all over square root of 30. So this is equal to 5 divided by square root of 30. 1.31. So probability of z greater than 1.31. Okay, so let's draw this one. Okay, 1.31 is here. So greater than, we have this. So therefore, our formula here is 0.5 minus this area. So 1.31 from the table is equal to 0.4049. So what is that equal to? 0.0951. So the probability that the average age group is greater than 44.2 years old is 0.0951.